Well, in the last section, we defined what the derivative of a function is, if it exists. And now we're going to discuss the algebra of derivatives. So in other words, if you know the derivative of two different functions at a particular point, you might know something about the derivative of the sum of their functions, or the product or the quotient of those two functions. So 4.2 is the algebra of derivatives. And our first theorem says that if we start with two differentiable functions, we start with f and g from the domain capital D into R, and they're both differentiable at one particular point in the domain, being x naught, then we know the following. The new function, which is the sum of the two functions, f of x plus g of x, has a derivative at x0, and that derivative is what we get by just taking the individual derivatives and adding them together. So f plus g prime of x naught is f prime of x naught plus g prime of x naught. And then, as you'll recall from calculus, the next two require a little bit more memorizing than that. And by the way, I'll go ahead and add in that f minus g prime of x naught would be f prime of x naught minus g prime of x naught. The second one, when you're multiplying the two functions together, we get fg prime of x naught is equal to, the way I like to think of it is the first times the derivative of the second plus the second times the derivative of the first. So you get f of x naught times g prime of x naught plus f prime of x naught times g of x naught. And the third one is the quotient. When you take f of x over g of x, or the derivative of that, which f over g prime of x naught, the derivative of f over g at x naught. This one takes a little more memorizing. I always think of it as the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. So that's just g prime of x naught times g of x naught times f prime of x naught minus g prime of x naught times f of x naught all over g of x naught squared. And of course, since g of x naught is in the denominator, it only works if g of x naught is not equal to 0. And in fact, this function only exists, the domain might be restricted. The function f over g wouldn't exist in points where g of x is equal to 0. Well, we'll just take a nice simple proof of part 1. You can look at the proof of 2 and 3 in the text if you like. And proving part 1, we're going to use sequences and theorem 4.1, which we talked about last time. Well, in order to use sequences in this type of a definition, we need to have a sequence xn that is such that all of the xn's come from the domain and they're not equal to x naught. So it's a sequence that is made up from d minus x naught, and it has to converge to x naught. Any arbitrary sequence. Well, f and g being differentiable at that point imply that using the theorem and the definition of the derivative, imply that this sequence, f of xn minus f of x naught over xn minus x naught, converges to the derivative. As does this, only with function g. G of x naught minus, or g of xn minus g of x naught over xn minus x naught. This sequence converges to the derivative of g at x naught. So that gives us two convergent sequences. And we know from long ago that two convergent sequences, if we come up with a new sequence where we add them term by term, they're going to converge to the sum of the two limits. So if I take f of xn minus f of x naught over xn minus x naught, just one term of this sequence, plus the term of that sequence, g of xn minus g of x naught over xn minus x naught, simply by properties of convergent sequences. We know that this new sequence, n equals 1 to infinity, goes to f prime of x naught plus g prime of x naught. And maybe to finish off the proof, I'll basically just repeat what we have here. And therefore, f plus g prime of x naught is equal to f prime of x naught plus g prime of x naught. And that's the proof.